Welcome everyone to Algebra 2, Section 3.2, Domain, Range, and Behavior. First, start with the warm-up. Warm-up 1, distance a car can travel. It's a function of the amount of gas in the car's tank. So, identify the independent variable and the dependent variable. The independent is what does not depend on the other thing. The dependent will be what depends on the thing. So, gas would be the independent variable, because gas doesn't necessarily depend on the distance you drive, but rather it would just depend on how much you put in the car and so many other things. And so in this scenario, that one is independent, whereas the distance you go would be dependent on the amount of gas you have in the car, because you only go so far for how much gas you have in the car. All right, and the real number system. So some examples of these. Let's start off with natural numbers. Natural numbers are the numbers you see in real life. So like the counting numbers, like 1, 2, 3. You don't count with negatives, you don't count with decimals, you don't count with 0. Whole numbers are all of those, but you also include 0. Integers are those, but you also include negatives now. So you have like -2, -1. I should do it ... beforehand. 0, 1, 2, ... Just keeps going on forever. Rational, we start incorporating fractions like -1/2 or -1/4. You also have 0. You also have 1/4. Let's say you also have decimals like 5.3. You could also have 2.2 repeating. So it can repeat or it can end. You could have like the square root of 16, for example. That's just 4, so that would actually fit all the way in natural as well. And then you have, last but not least in this category, is irrational. And irrational are decimals that do not end or repeat. So like the square root of 17, it's not a perfect square. It doesn't end, nor does it repeat, like 2.2 did. And like pi would be another good example. Another one might be, let's say, 5.23847 ... just keeps going with no repetition. All right, now on to the new stuff. Interval is part of a number line without any breaks. So it's just saying, hey, from here to here. And we're going to have 3 different descriptions of intervals here. One is all real numbers from A to B, including A and B. So we're saying, hey, every number from this to this, and we want to include those two. So this is a finite interval because it does, in fact, end. And so we could write it as an inequality that the lower number A is less than or equal to X, and then the bigger number, B in this case, is greater than or equal to X. In set notation, you do the same thing. You write this inequality, but you put X such that. That's what that little bar means. It means such that. And then you put this brace at the beginning and the end. And then interval notation, it's like a parenthesis or a bracket. So whether it's a parenthesis or a bracket depends on whether or not it includes that number. So in this case, because A and B are part of the interval, they're brackets. If A was not part of the interval, like it stopped right before A, then it would be a parenthesis. Next one is all real numbers are greater than A. So that would be an infinite interval because it never ends, because it just continues on for all the numbers that could be bigger. So this you write as an inequality again. X is greater than A. Set notation, same idea. Write the inequality, but put the X such that first and braces around it. The interval notation, because A is not part of it, you just only want numbers that are bigger than it. Use the parenthesis at A, comma, and it goes all the way to infinity. And you don't have to put positive infinity if you don't want. We assume it's positive unless you denote or write otherwise. And then the third interval we're going to be talking about here, these are just kind of different examples to highlight different things, by the way, is all real numbers less than or equal to A. So this will be another infinite interval because it's any number that could be less, so it never ends. And you just say X is less than or equal to A, and you put the X such that, then the inequality, and a couple braces. And the interval notation would start with negative infinity this time because you go the lower number first on all these, by the way. Comma, and then it does include a because it's or equal to. So how do you read these? Using these up here. So we're just going to use that first one above. So the inequality would be read as x is greater than or equal to a and less than or equal to, I'm going to have to make more room, b. Set notation, you would say the set, oops, not the t, the set of real numbers. Now, the real number system, which we talked about earlier, is actually abbreviated like this. It's an R with 2 lines, and it goes like that. So I want to write that off to the side real quick. Hey, that means the real numbers. And a quick reminder from our warm-up, real numbers are all of our numbers that aren't imaginary, essentially. So unless it has an I in it, it's a real number. So a set of real numbers, any number that's not imaginary, such that, and then it's all of this from up there, just down there. I'm not going to write all of that again because that is too much work. And it will not fit on my line. So you'd say the set of real numbers such that x is greater than or equal to a and less than or equal to b. And interval notation is going to be all real numbers from a to b. And then you would either say including or not including, depending on what the case is. In this one, it is including a and b. And like I talked about earlier, I want to note that the bracket means that it includes the number, and the parenthesis means that it does not include the number. I forgot a U there. Pardon me while I blow my nose. I want to mute for a second. All right, continuing on. So, talking more in depth about finite intervals and just using a couple examples here. This first one, see if you can figure out what this finite interval is. If not, maybe do the first one with me and do the second one on your own. So it's -2 to 3, we can see, and it includes -2 and 3 because they're closed circles. So you'd say, hey, -2, the smaller number, is less than or equal to x, which is less than or equal to 3. So you can read it that way, or say that, hey, x is greater than or equal to -2 and less than or equal to 3. In set notation, you would say, hey, here's the same inequality, but we're just going to put x such that before it. And everything else is the same, and you add braces and you're done. The interval notation, I'm going to go with purple this time. Interval notation would be -2, 3, and they both have brackets because -2 and 3 are included. This one, once again, I would encourage you trying it on your own. Now, the inequality would be -2 is less than x, but not or equal to, because it's an open circle, so it's not included, is less than or equal to, so not x, but 3. Set notation, same idea, x such that -2 is less than x, which is less than or equal to 3. And the interval, -2, 3. -2 would have a parenthesis because it's not included, and the 3 would have a bracket because it is. All right, infinite intervals. The inequality for this one, we'll always put the variables first on these. So x, and it is less than or equal to 2. So the set notation would be x such that x is less than or equal to 2, with braces around it. And the interval notation would be negative infinity, which is where it goes on the left. And that'll be a parenthesis because it can never actually go to negative infinity because it's not a number. It is really just a concept. So infinity or negative infinity will always have a parenthesis. Comma 2, which will have a bracket because it's or equal to it. Recommend trying your next one on your own. It is x is greater than 0, but not or equal to it because it is an open circle. The set notation would just be x such that x is greater than 0. And the interval would be 0, comma, infinity. You could put positive infinity if you want. Both are parentheses because neither are actually included because you can't get to infinity because it's a concept, not a number. And 0 is an open circle, so it's not part of it. All right, consider this. What numbers are in this interval? Well, since the entire number line is highlighted, it's every number, so it's all the real numbers. Any number you can possibly think of that's not imaginary. Now, using interval notation, once again, that's the parentheses and bracket one, how would you represent this? Well, it goes from negative infinity all the way to positive infinity and everywhere in between them. All right, this one on number 2 is a little bit different. This one is every single number with an exception. So it's all the real numbers except 0, because 0 is not included. So this one in interval notation is going to be a little bit different because we're going to have 2 different parts. So we'll have negative infinity all the way up to 0, and then we also have 0 to infinity. But it doesn't include 0. So what to put in between is this union. And so it's like a U there. But you don't put like the tail on the U like you might. And when you write, it's kind of more like the parabola U. So that's saying, hey, it's not only this, it's also this. And once again, that stands for union. It just means both of these. Or if you have multiple, 3 even, you would do all 3. So end behavior. Let's see, I'm going to blow my nose one more time here. All right, end behavior. So what does the symbol mean? Well, it means infinity. Let's make sure we know that. All right. So let's talk about this little table here, so to speak. So this talks about the end behavior. What we mean by end behavior is what are the ends of the graph doing. So what are the left and the right end of the graph doing in each of these? So the left, the right, the left, the right, left, the right, so on and so forth. So how we do this is we say, okay, as x values, so as it goes left and right, as it goes all the way to left, as it goes to negative infinity, what's happening up and down? What's happening with our f of x? Which, a reminder, is really y. And we say the same thing going to the right. Hey, as x goes to positive infinity, or just infinity, all the way to the right, what's happening with my y values again, my f of x? So whenever you have an odd function, aka the leading coefficient has an exponent that's odd, or you can think of it as the highest exponent in the whole equation or function is odd. So, and the leading coefficient is positive, we'll always have this scenario where the left side, as it goes to negative infinity for the x, the y's or f of x will also go to negative infinity. As the x goes to positive infinity, the y's or f of x will always go to positive infinity. Quick example would be like y equals x cubed, or f of x equals x cubed, which is really the same thing. So as we can see here, the coefficient is positive because it's not a negative there, and then the highest exponent is 3. Let's say, hey, when it's odd and it's negative, so an example of this would be like y equals, or f of x equals, negative x cubed. So the highest exponent is still an odd number because it's 3, and the leading coefficient this time is a negative. So as x goes all the way to the left and x goes all the way to the right, we see it reverses. That it goes up as it goes to the left, and it goes down as it goes to the right. So we say, hey, it goes to positive infinity forever up, and it goes to negative infinity forever down. Then if it's even, we notice they're going the same direction. Either they're both going up or they're both going down. So how we know if they're both going up or both going down, whereas an odd, they're going one each direction, is we say, okay, well, is our leading coefficient positive or negative? So a good example here would be like f of x, or y equals x to the 4th. You could have done any even exponent. And this one is a positive, so it fits this description. And we say as x goes forever to the left, it goes up. As x goes forever to the right, it goes up as well. So they both go up. Whereas if it's like maybe like f of x equals negative x to the 4th, it goes down. So it goes to negative infinity and negative infinity as x approaches both negative and positive infinity. We're going to refer back to this quite a bit because right here we're describing the end behavior of this graph, just saying, hey, where are the ends going? So we have this one, f of x is equal to x to the 7th plus 3x to the 4th minus x squared. And we're saying, hey, as x goes to negative infinity, what's f of x doing? And as x goes to positive infinity, what's f of x doing? So we say, hey, what's our highest exponent? Well, it's 7. So 7 is odd. And we say, okay, is the leading coefficient, the number with this x to the 7th, positive or negative? Well, it's positive. So that tells us, hey, follow this scenario. So as x goes to negative infinity, f of x will go to negative infinity. Oh, I should have put equals, not equals. My apologies. Arrow, because it goes to that. It isn't equal to that, it goes toward it. And as x approaches positive infinity, the f of x, or the y, will go to, or equals again, darn it, positive infinity, or just infinity. And in words, it basically means as the x values decrease without bound, aka go forever with no boundary, then the f of x or y values also decrease without bound, or increase without bound. So basically increase and decrease forever. Now, how this is helpful, you might be wondering, like, Mr. Crosswell, when are we going to use this? That's a good question. It is helpful when we're trying to graph random functions out of nowhere. So later in the math we'll be doing, even in this chapter, it'll be helpful. And later this year, real life, basically, it will help us do other real life things easier as well. And what I mean by that is where that math already applies for real life purposes, that'll make those applications that much easier. So it's not necessarily a separate real life application from those, just makes those easier. This page is just a page for you. It's a reference sheet. I'm not going to discuss it, but it just kind of discusses, hey, here are these different examples of interval notation, description of that, and the graph. All right, here's some practice that we can do over this. I encourage you to do as much of this on your own as you can. I think it'd be a great idea for that to be the case. So, domain and range of the function as an inequality. and using set notation and interval notation. So domain, those are the x values and the range of the y values in case you don't remember. If you don't remember or you have a hard time remembering it might be good to write that down. So for this graph, okay, what are the x values in it? Well, it's going forever to the left and it's going forever to the right. So that's positive and negative infinity. So it goes from negative infinity is less than x is less than infinity. Or x is greater than negative infinity and x is less than infinity. Because it goes all the way to the left, all the way to the right with no interruptions. So the set notation then is just going to be x such that, and then rewriting that inequality with the braces. The interval of that would be negative infinity comma infinity with parentheses. They can't reach infinity and negative infinity. The range, those are the y values for saying, hey, how high or low does this go? So it goes down forever to negative infinity, but it doesn't go up forever. The highest it gets is 0. So our range is going to be y, not x, because we're talking about the y values, is less than or equal to 0, because it's 0 and anything lower than that. Sorry, I'm not feeling the best, so that's why my voice sounds different than normal, if you hadn't noticed. Set notation would be y such that y is less than or equal to 0. The braces, that was an atrocious brace. That was better. And the interval notation would be negative infinity first, comma 0, and 0 has a bracket. For end behavior, as x is going forever left, negative infinity, the f of x is going to negative infinity. And as x is going to positive infinity all the way to the right, then f of x is going forever to the right. All right. Now, what does all real numbers x such that x is greater than 2 look like in symbols? So you see the word such that, and that should tell us, hey, we're doing this set notation, because the such that is this little line. So I already know I'm going to do x such that, and I see x is greater than 2. So I say x is greater than 2. Put in braces, and congrats, we did it. Woo! All right, example 3. For the given function and domain, draw the graph and identify the range using the same notation as the given domain. So we're told this function f of x is equal to 3/4 x plus 2, but we're only told to graph on the domain negative 4, comma 4. So we're not wanting to graph everywhere. We're wanting to go to negative 4, including it, and positive 4, and including it because they're brackets. So my b is 2, so I begin with 2, and I go up 3, right 4, or down 3, left 4. And once again, I'm not going to put arrows on there because it only wants me to stop there according to my domain. So now we can say, hey, what's my range from this? And it wants me to put it in the same notation, so that's interval notation. So it's saying, hey, what's the lowest it goes and what's the highest it goes? So we see the lowest in the graph it goes is -1, and it gets to -1 right over here. The highest it goes is up here, and it gets to 5. Number 4, graph the function f of x is equal to -x minus 2 with the domain x such that x is greater than -3, and identify the range. Okay, so -x minus 2. So start off at -2, and if the negative slope, -1 slope, I'm really going down 1, right 1. Continuing on. And it's saying, hey, we want the ones that are greater than -3, so meaning I'm going to be starting at -3, but -3 is not included. So I'm going to make an open circle there and draw the arrow going this way because those are included, but 3 is not included, negative 3 is not included, and anything to the left of that is not included. So now for the range, in the same notation, I'll be using set notation, so I'll do a y such that, and I say, okay, what's happening to y? Well, the highest it is not quite to 1, but it's like open at 1. And the lowest it is, well, it goes forever down. So we say y is less than not negative, but positive 1. Because it doesn't quite get to positive 1, but it's everything lower than that. We can't put 0 because it is higher than 0 over here. All right, word problem. Woo, gonna blow my nose one more time. Okay, continuing on. A candle 6 inches high burns at a rate of 1 inch every 2 hours for 5 hours. Graph the function and answer the following questions using interval notation for domain and range that models this. So it might be a good idea to go ahead and graph it. It starts off at 6 inches at 0 hours, and then after 2 hours it burns 1 inch. So it's down to 5, and down to 4, and so on, so forth. And it only burns for 5 hours, so I'm going to stop it right there, because it doesn't keep burning then, so I'm not going to put an arrow on it. Now, if it were to keep burning, then we might, but it's not. Now, this candle is burning at how many inches an hour? Well, you could divide 1 inch every 2 hours, so that is 1 over 2, or 0.5 inches an hour. Now, since the candle burns for 5 hours, the domain is restricted to 0, 5. That's the farthest we go to the right, because that's the farthest it burns. So this is a scenario, real-life example, where we might use a restricted domain, saying, hey, it's only this. Then the range on this one would be, let's say, what's the highest? Well, it's 6. The lowest is 3.5. So you put 3.5 or 7/5 or 7 halves or 3.5 with the bracket, because it does get to 3.5 inches, 6. It's the highest it ever is at the start. And you should put them least to greatest. Identify the end behavior of these functions. This is separate from number 5. So this is going back to the last thing we talked about in the notes before this. So this one on A, we say, hey, highest exponent's 1, so that's odd. Leading coefficient is negative, so it's negative. That tells us, hey, as x approaches negative infinity, f of x, or the y values, would approach positive infinity or just infinity. And as x approaches positive infinity, as x goes all the way to the right, the y values, or the f of x, or the graph, goes forever down. An example B, it's an even highest exponent as 2, and it's a positive leading coefficient with that exponent, the x to the second. So the x approaches negative infinity, goes all the way left. The f of x, or the y values, go all the way to up, positive infinity. And as it goes all the way to the right, it actually does the same exact thing, also goes all the way up. All right, that is it for section